Standard cartographic maps of the Los Angeles Basin present a highly reductive geometry. They illustrate a sprawling, uniform, two-dimensional plain. But that cartographic abstraction ignores the physical reality. The region is actually a complex geomorphic amphitheater, shaped by active tectonics and defined by sharp vertical relief. To understand how this topography dictates the city's architecture and infrastructure, we have to measure the exact visual and structural relationship between the Mount Lee promontory, home to the Hollywood sign, and the alluvial plains below. We cannot rely on standard commercial GPS to make this assessment. The World Geodetic System of 1984, or WGS-84, is an Earth-centered dynamic datum. Because it shifts to account for the planet's continuous structural changes, it fails to provide the stable, localized vertical constraints necessary for millimeter-accurate urban comparison. Instead, civil engineering in seismically active California requires the North American datum of 1983. NAD 83 is a plate-fixed horizontal baseline anchored directly to the North American plate. This filters out the constant tectonic drift that would otherwise skew short-term static site comparisons. Calculating true sightlines across this basin is not a simple exercise in drawing a line on a flat map. It requires solving a three-dimensional geodetic problem that accounts for the curvature of the Earth and the specific gravitational anomalies of the terrain. We begin by defining an unmoving geodetic anchor point. For this study, that precise location is the exact centroid of the Hollywood sign structure. The terrain immediately surrounding the sign is steep chaparral, with a gradient frequently exceeding 45 degrees. Because the structure sits on this near-vertical face rather than a flat plateau, it maximizes the solid angle presented to viewers in the basin below. The base of this specific structure locks our reference point at an exact elevation, 1,570 feet above mean sea level. To ensure that measurement holds across the city, we must standardize our vertical data to the North American Vertical Datum of 1988, or NAVD-88. The predecessor model from 1929 was based on a simple best-fit average of coastal tidal stations. Over the following decades, extreme crustal motion deformed that original baseline. The transverse ranges experienced rapid tectonic uplift, while the lower Los Angeles Basin suffered massive groundwater subsidence. These opposing vertical forces rendered the 1929 model inaccurate. Elevation in Southern California is a dynamic gravitational measurement. Only by strictly adhering to the NAVD-88 geopotential adjustments can we calculate precise cross-city vertical differentials. This graph plots the exact latitudinal and longitudinal coordinates for two lowland locations onto a wireframe representing the Los Angeles Basin, the original farmers market at Site A, and 6401 Wilshire Boulevard at Site B. Despite 0.8 miles of horizontal distance separating them, there is a negligible elevation difference. Site A sits at 175 feet above sea level, and Site B sits at 182 feet. This extreme flatness is the result of a distal alluvial fan. Over millennia, storm runoff from the northern canyons carried loose sediment out into the basin, depositing massive layers of silt and sand that leveled the topography. Because of this low-gradient depression, the area historically acted as a natural sink. It became the primary pooling zone for water and subsurface asphalt. Moving our observation point directly north to the intersection of Sunset and Vine reveals a completely different topographic zone, sitting at an elevation of 368 feet. This abrupt 200-foot gain marks the proximal piedmont. As high-velocity canyon streams exited the steep mountain channels above, they immediately dropped their heaviest debris, creating an elevated shelf at the foot of the hills. The city's elevation profile is dictated entirely by this subsurface sedimentary deposition. It creates a strict topographic stratification, separating mid-city commercial corridors into a low orchestra pit, while placing Hollywood on an elevated mezzanine viewing tier. This diagram illustrates the mathematical requirement for establishing spatial relationships across this varied terrain. We must merge Haversine surface distance formulas, which account for the curvature of the Earth, with Euclidean 3D vectors to account for the 1,388-foot elevation delta. Applying this formula to our Wilshire origin point creates a precise 5.77-mile 3D slant range connecting the lowland basin to the Mount Lee anchor. For an observer on the distal plane, this results in an incredibly shallow angle of inclination, just 2.61 degrees. Shifting the origin to the Sunset and Vine intersection drastically alters the geometry, calculating out to a much shorter 2.52-mile slant range. And because this vector originates from the elevated Piedmont zone, the resulting lookup angle nearly doubles to 5.18 degrees. A 2.61-degree angle creates a highly fragile line of sight. From the Wilshire corridor, even a modest 4-story apartment building can completely occult the mountain peak. But the 5.18-degree angle from the Piedmont clears most low-rise obstructions, giving the landmark structural dominance over the local grid. This diagram demonstrates the Fresnel zone. This is the elliptical spatial clearance around the direct line of sight required for uninterrupted microwave and radio data transmission. Because the Wilshire vector is bound by a shallow 3-degree angle, standard high-rise developments along that corridor easily intersect the lower bounds of the Fresnel zone. Any structural intrusion here causes severe signal diffraction. The Sunset and Vine vector avoids this interference. Its steep 5-degree angle ensures a robust telecommunications connection to Mount Lee, lifting the transmission path completely free of the ground level clutter. These spatial vectors also interact directly with the region's thermal inversion layer, a weather phenomenon that routinely traps particulate matter between 1,000 and 2,500 feet. Viewing the peak from the Wilshire Basin incurs a massive atmospheric extinction penalty. The nearly 6-mile vector forces light through the widest possible horizontal cross-section of this particulate haze, severely reducing visual contrast. By contrast, an observer standing at the 368-foot elevation of Sunset and Vine is physically lifted above the densest ground-level smog. At the same time, the shorter slant range cuts the required atmospheric path length in half, yielding consistently superior visibility. True urban topography is an active 3-dimensional spatial system. The unseen sedimentary geology beneath the streets establishes the precise math that dictates modern line of sight, structural prominence, and telecommunications viability.